Each session will be chaired by the session chair. So I hand over the microphone as well as the operation of this session to the session chair, Professor Anirban Pathak.
Thank you, and I welcome all to the first technical session of the conference. And since it's going almost 15 minutes late, I'm not giving a long introduction to the speaker, and speaker is known to all of us. So first speaker is Professor Shivashish Ghosh from Institute of Mathematical Sciences, Chennai, and he will speak on repeater-based optimal quantum teleportation in noisy scenario, the case of qubits. So I would like to request Shivashish that to deliver his lecture.
আর এইটা ওইটা ঠিক আছে okay so let me thank the session chair and let me also thank the organizers to giving me this opportunity to talk about our work. So this is a work which I have done. Well, the first work is still a bit of modification is going on with a former postdoc in our group, Arko Prabhu Ghoshal. Then okay, so this is, as I said, this is Arko Prabhu Ghoshal, who was a postdoc in our group. Jatin Ghai is a PhD student. Tanmay Saha, also a PhD student, and Mead is a postdoc in Antonio Assin's group. So here, what we are, okay, maybe I'll come back to this. So what? So these are our group members. Not everybody is involved in this work. Jatin, then Tanmay, and yeah. So and this is Arko Prabhu, and this is Mead. So basically, what we are looking at is that the standard teleportation scenario where two parties, Alice and Bob, they share some state, entangled state, which may be, I mean, maximally entangled, non-maximally entangled, it may be pure, mixed, etc. So we know what is the best teleportation scheme to get the best teleportation fidelity. The question is, if we have a network scenario like entanglement swapping scenario where you have more than two parties like Alice Bob and then Bob Charlie and so on and so forth, when they share some noisy entangled state, what will be the best option to share the best teleportation channel between one end and the other end? Is it the standard teleportation protocol which will work, or we'll have to do something else? So here what we are going to talk about is that no, you'll have to do something else. The standard teleportation protocol most of the times will not give you the best option. Okay, so as I said, given any 2QD state of two d-dimensional system, then the shared between Alice and Bob, then the optimal teleportation fidelity for this state rho is known to be dependent on the optimal singlet fraction, which is this one, this f of rho. So this Carly f rho, which is the optimal teleportation fidelity, is a linear function of this optimal singlet fraction. Okay, so which is basically the best overlap between your state and a maximally entangled state. And generally, what one needs to do is to perform measurement at the receiver's end in the Bell basis or in higher dimension generalized Bell basis. So, as I said, in a network scenario, the question is whether it is a straightforward extension of this scheme, or we'll have to do something else. So what we'll talk about here is the special case where the dimension D is 2, and we'll try to show that yes, in noisy scenario, and when you have a network case, then you need to have special attention which will give you the better performance. Okay, so this is the plan of my talk. So I'll briefly mention about quantum teleportation, although everybody knows. So optimal teleportation is 2-qubit state, and then optimal distribution of teleportation channel via local operation classical communication. And then I'll go to the 3-node scenario where Alice, Bob, and Charlie are working together, and then the optimal LOCC protocol. And then we'll talk about the complexity if we want to go beyond the 3-node scenario. And then finally, we'll talk about the the teleportation fidelity in n-node scenario, where you can get the same teleportation fidelity, optimal fidelity, with less entanglement in the channel. And then I'll summarize the result. Okay, so quantum teleportation, as you know, is this is Alice and Bob. So Alice has a data qubit, so it is an unknown state, and then Alice and Bob share some entangled state. So Alice will perform some joint operation here, some measurement, and then send the classical information to Bob, and Bob will do something on his system to get the teleportation. Okay, so it's like this. So Alice's input, the shared state between Alice and Bob, and by LOCC, they will have this kind of state. Okay. So, so this is the standard teleportation scheme for 2-qubit state. So, these are the 4 Bell state measurement and the corresponding outcomes, and then Bob will have to apply these rotations. Okay. So then, so let me go to the optimal teleportation of 2-qubit case. So here, why is it not? Okay. So the standard figure of merit is this, the average teleportation fidelity. So basically, in this scheme of teleportation, this is the state which Bob will have finally, and then you take the overlap with the input state, and then you take the average over all the input state. That will give you the average fidelity. Okay, and one can basically apply the local unitary transformations on Alice and Bob's side to maximize this fidelity. Okay, right. And so, but this is a specific kind of transformation, local unitary. You can now enlarge the transformation. So, for example, what you can have is, because the singlet fraction is the, what you do is you take the maximum overlap of your state with a maximally entangled state, and therefore this fully entangled fraction or singlet fraction is related to this teleportation fidelity through this process, because your dimension is 2 here. Okay, and one can show that a state is 2-qubit state is useful for teleportation under standard protocol if and only if these the singlet fraction is greater than half. Okay, that means it performs better than a classical one. Okay, now you can enhance even more. So what you can do, you can have your state, apply LOCC, local operation classical communication, and take the singlet fraction, the optimal singlet fraction. So you maximize over all LOCC now, and that will give you the fully entangled fraction. And this optimal teleportation fidelity again is related. This optimal teleportation fidelity is 2 times this fully entangled fraction plus 1/3, and this is the best that you can do. Okay, so any 2-qubit entangled state is useful for teleportation in the sense that I can so Alice can perform a filtering operation, 2-outcome filtering operation, which is a POBM, and then Alice and Bob can bring, so this is one-way LOCC, they can bring the state into this form, and then the sigma AB, and then they apply the standard teleportation, And if this filtering fails, then Alice and Bob will share with a pure product state, and which will have the singlet fraction half. Okay, so this is the way to get to show that arbitrary 2-qubit entangled state, pure or mixed, is useful for teleportation, because in that case the singlet fraction is greater than half. Okay, so this optimal teleportation fidelity of any 2-qubit state, it can be expressed in this form. So this is your, so this is the singlet fraction. So basically with p0 probability, when the filtering is successful, you have this singlet fraction plus 1 minus p0 by 2, because in that case they share this pure entangled state. And this is the state, the sigma AB, which Alice and Bob will have once Alice applies a particular filtering operation. Okay, and this is just one way LOCC from Alice to Bob is sufficient. Right. Okay, so now okay, so now the question is that this optimal teleportation fidelity for the 2-qubit state, as I said, if it is any entangled state, they will have to Alice will have to apply this filtering operation. But generically, to optimize this quantity, this is the singlet, I mean this is the fully entangled fraction, is not easy to do. So one can basically figure it out by doing this semi-definite programming problem. So you maximize this quantity subject to these constraints. Okay. Now there is an upper bound on this optimal singlet fraction, which is given by this 1 plus negativity of the state. This is I am talking about 2-qubit state, and which is also upper bounded by 1 plus this concurrence, which is this entanglement of formation in the state, by 2. Okay. Now this bound can be achieved provided your state you choose rho AB in such a way that I take the partial transpose, and basically this is this lambda minimum is the smallest eigenvalue, corresponding eigenvector is phi, and this is a maximally entangled state. Okay, so in this case you can show that this bound is achieved, this one and this one are same. Okay, so for example, if you have Bell diagonal state, that means if this rho AB is mixture of Bell states, or if it is a pure entangled state rho AB, then this bound will be achieved. Okay, so let me go to this optimal distribution of teleportation via LOCC. So the question is, so we know that this optimal teleportation protocol for a 2-qubit state, just what I mentioned, but we know that this protocol is of course state dependent, because the filtering operation is state dependent, and one-way LOCC is also sufficient. The question is, can we extend this simply to the network scenario where you don't have only two parties, more than two parties, Alice, Bob, Charlie, etc. So n node scenario where the sender wants to establish optimal qubit teleportation channel, that means between sender and the receiver, they want to have this shared channel. Okay, right, and so basically this is a kind of repeated scenario. Okay, so between the sender and receiver, you have different nodes, and through this repeated process, we want to send information from sender to receiver. And the question is, what is the best teleportation scheme in such a scenario? Okay. What is the problem? Okay, so this is the this is the basically scenario. So you have different nodes. So between Alice and first one, N1, you have a state rho 1. Between N1 and N2, you have a state rho 2, so on. And between N and nth party and Bob, you have this rho Sn. So these are the basically the nodes. And so the question is, by LOCC, one can have operation here, 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 etc., and then communication. So they want to share the state sigma between Alice and Bob, so that this sigma has the best teleportation fidelity. And people have done several works in this area, although the complete answer is still not known, okay, in general. Okay. So what we can do is, let's take the simplest case. So simplest extension where Alice, Bob and Charlie, again we are talking about this. So here this Alice and Bob, they share this row AB, row AB1, and between Bob and Charlie this sigma B, B2C, and they apply some local operation which may be measurement or something else, and then they collaborate so they can have communication, classical communication, so that ultimately they will come up with these kind of state tau AC corresponding to the outcome A with this probability QA. So that this teleportation fidelity, or you can say the singlet fraction, optimal singlet fraction, is equal to, which we know that this is basically over all lambda, which is LOCC on Alice, Bob and Charlie, and that has to be greater than half. So this is the main goal, how to do that. Okay. So let me put the objective here is that the spatially separated parties, namely Alice, Bob and Charlie, and they share arbitrary state row AB1 with dimension maybe 2 or greater than 2, and BC again dimension maybe 2 or greater than 2. So here we are taking same dimension, but you can do in principle different dimension. And all these parties have the freedom to do this LOCC, local operation classical communication. And the task is to distribute entanglement between Alice and Charlie such that is fully entangled fraction is maximized over all three-party LOCC, and it should be strictly greater than, of course, the classical bound is in this case 1 upon D. Okay. So that is basically the idea. Okay. So how to implement such a scheme? So in general, it is very difficult to answer. We don't know how to do that. Okay. So one can have one way LOCC, two way LOCC, or n round LOCC, and of course we know that in principle we will get better if you do if there is no restriction on the round of LOCC. So for n round LOCC, whatever you get as best fidelity, you will have even a better one if you have no restriction on the number of rounds. Now this is also known that any LOCC is a special case of what is known as separable operation. So on individual parties, I am applying some quantum operation, okay, but of course the converse is not true. So there are separable operations which are not implementable by LOCC, and one can show that if Alice and Bob share this row AB1 and Bob and Charlie share this sigma B2C, then the best singlet fraction under all such set, that means the separable operation, which is basically this one. So this eta is tensor product of rho and sigma. So you apply this LOCC lambda on that eta and then trace out B part, because ultimately we want to have best teleportation channel between A and C, and then you take overlap over all such maximally entangled states. So anyway, so one can cast this problem into again a semi-definite programming problem, and as I said, this bound singlet fraction is generally greater than or equal to the LOCC bound on the singlet fraction. And you can look at our paper to get to see all the details about this optimization problem. Okay. Yeah, so I'll not go through all these things. This is all there in our paper. And so basically, what one can prove that this fully entangled fraction, it has to be greater than 1 upon D if it is a quantum teleportation, and of course a classical one, we know that it has to be 1 upon D because classical singlet fraction, because in that case Alice and Charlie can just share a product pure state to have this 1 upon D value. Okay, good. So there is a sufficient protocol which states that this one-way LOCC from Alice to Charlie and another one-way LOCC from Bob to Charlie is sufficient. Between Alice and Bob, there can be multi-way LOCC, but this protocol is sufficient. And even as I said, because the SAFE operation includes the SAFE, LOCC operation, even the optimization problem for SAFE operation is still difficult. Okay, and so basically, as I said, these under the SAFE operation, the problem of finding the optimal singlet fraction, it can be cast as a semi-definite programming problem, but still it is difficult to solve. Okay, so this is what I said. Between Alice and Charlie, you have one-way LOCC through this kind of operation. Between Bob and Charlie, you have again one-way LOCC involving this kind of operation, and then they collaborate to share some state tau with this probability Q, and then they can use this as the teleportation channel. Okay, good. So there are upper bounds on this optimal teleportation fidelity. Okay, so these upper bounds, like, so we consider, for example, this A and B, Alice and Bob, they share a 2-qubit state, rho AB1, and Bob and Charlie, they share another state, let's say sigma B2C, is in the D dimension 2. And one can prove that on this singlet fraction, optimal singlet fraction between Alice and Charlie for sharing this rho and sigma, it is upper bounded by minimum of this quantity F1 star and F2 star. So what is F1 star? F1 star is the minimum of the optimal singlet fraction of the state rho AB1 and sigma B2C. So basically what it tells you that between Alice Bob and Bob and Charlie, you have two noisy states. Use that channel which has best teleportation fidelity. Maybe it is for this rho AB1 for the teleportation. So you can use that channel to send the state of the part of the Bob which is shared between Bob and Alice, and that will give you the best fidelity. So that is one part, and the other part is, this is a kind of bound on the concurrence of on the state shared by Alice and Charlie finally. Okay, so this is the concurrence of rho AB1 times concurrence of sigma B2C. So this bound, singlet fraction bound between Alice and Charlie, is upper bounded. This is upper bounded by minimum of these two quantities. It may happen. So basically, generally we don't have any ordering between F1 and F2 for genetic states, rho and sigma. So sometimes F1 can be greater than F2, and sometimes F2 can be greater than F1. Okay. So this is a bound. Question is whether this bound is achievable. How tight is this bound? So let us look at that. Okay. So this optimal teleportation protocol for the 3-node scenario which we are considering here. So this is the case. So what you can do is, the intuitive idea, as I said, is that, so suppose this Bob Charlie share a higher fidelity state. So the singlet fraction of rho AB1 is less than equal to singlet fraction of sigma B2C. So first make this optimal post-processing on sigma B2C. So that means you make this post-processing, that means this local filtering, to get the optimal teleportation fidelity between Bob and Charlie, optimal teleportation channel, and after that you can send the state of B1 through that channel. Okay. Unfortunately, this is generally not the optimal protocol. Okay. So in case you have this noisy rho AB and noisy sigma, this is not the best protocol. Okay. So now let us look for, I consider two protocols. The first one I call P1, where Bob first performs the 2-qubit projective measurement in any maximally entangled state, maybe well basis or something else, and then classically communicate the outcome to Alice and Charlie. This is a 3-node scenario. Okay, and then Bob's system is discarded. So Alice and Bob will have some channel, some entangled state, and then one-way LOCC is performed from Alice to Charlie to achieve the teleportation. So this is which I call protocol P1, which is the standard teleportation, you can say. Second one is that Bob first performs a 2-qubit projective measurement, but this is not in maximally entangled basis. They perform in some non-maximally entangled basis measurement, okay, and communicate the outcome again, like here, Alice and Charlie. And after that, Bob's system is discarded, and then LOCC is performed from Alice to Charlie or from Charlie to Alice. right. So, this is a measurement basis in a non-maximally entangled state. Okay. There are examples where this scheme will provide you better result compared to this scheme, to standard teleportation protocol. Okay, good. So, this is what. So, for example, if I want to look at the optimal singlet fraction between Alice and Charlie, where it is equal to this F2 star. So, F2 star is this 1 plus product of concurrences of rho and sigma divided by 2. So, that is also one of the bounds, upper bounds. So, let us say Alice and Bob share a pure entangled state, and similarly Bob and Charlie also share a pure entangled state. Then they can, so Bob can perform a joint measurement in this maximally entangled basis, and then also Alice and so communicate the result. Then Alice and Charlie can apply some unitaries, local unitaries, and then ultimately they will have they will share this pure entangled state, for which if you calculate the optimal singlet fraction, it will turn out to be like this: 1 plus C of psi 1 times C of eta by 2. Okay. So, this is a scheme where these two are pure entangled states, and the measurement is this Bell state measurement. Okay. Yes. The other case where this optimal singlet fraction is same as the the minimum of the optimal teleportation fidelities for rho and sigma. Rho is shared between Alice and Bob, and sigma is shared between Bob and Charlie. So, let us say I take the state of rho AB as this noisy state. So, psi is this pure entangled state, and then you mix it with this product state for these parameter values, and in sigma you take it to be projection on a pure entangled state. Okay. Yes, 5 minutes. Okay. So, there you can apply this protocol P2, where Bob performs a projective measurement not in the Bell basis, but in non-maximally entangled basis. So, I have given here one basis element, but you can change this here with this the 0 1 and 1 0, and then interchange this coefficient, you will get the full basis, and then classically communicate. So, Alice can perform a 2 outcome POVM. After that, Alice can perform 2 outcome POVM, and then does classical communication to Charlie, and then for certain parameter values, this P alpha beta delta, one can show that this bound is achieved for this case. Okay. So, right, and of course, the one can get even a better bound on the optimal teleportation fidelity compared to this minimum of this F1 star and F2 star. For example, when rho and sigma both are a mixture of Bell states. Okay. Okay. So, and as I said, Bob's measurement in the maximally entangled basis is not always provide you the best. There are occasions where Bob can apply measurement in non-maximally entangled basis. Okay. And sometimes this one-way LOCC from Bob to Alice may not be also sufficient. So, let me skip this part, and yeah. So, here you see that these are these F1 star, F2 star. So, for this particular noisy state that I mentioned earlier, which is maybe I'll just okay, maybe I'll just tell you briefly. So, here the noisy state is this mixture of a pure state and a pure product state, pure entangled and pure product state with this coefficient P, mixing coefficient, and one can show that in some regime this P2 protocol, where Bob performs measurement in non-maximally entangled basis, it gives you better performance compared to the standard protocol. Okay. Yeah, so this is the measurement basis that the Bob can perform. Okay, so complexity, if I want to go beyond this thing, so because that will be again a semi-definite programming problem, but still it is quite difficult because it is not a, so the semi-definite means that your search space is a convex set. So in this case, the search space may become non-convex set, and therefore it becomes more difficult. Okay, if we have more than three parties. So let me briefly mention the work where we have extended. We could manage to extend for more than three parties, n party case, in a scenario where so okay, so let's say Alice, Bob, Charlie, etc. So one of the nodes, one of the link is a noisy entangled state, and other links are pure entangled states. Let's say, so this is the, so I have shown you this picture earlier. So one of the link is a noisy mixed entangled state, and the other links are pure entangled state. In that case, what one can show is that, of course, in the standard entanglement swapping case, um, if the pure entangled states are maximally entangled state, then one can basically, the teleportation fidelity between the first, I mean the receiver and the sender, that means the two end nodes, will be given by the optimal singlet fraction of the noisy entangled state. That is the usual thing. Here what we have shown is that the same optimal teleportation fidelity one can achieve even with these non-maximally entangled pure state, okay, for certain regime of parameters. So with less entanglement, you can achieve the same goal. And so I'm not going into all the details. So basically, this optimal singlet fraction, one can show that this is again upper bounded by Fs and Fc. So Fs is this minimum of this optimal singlet fractions for individual states, and Fc is this given by this 1 plus product of the concurrences. So what we have shown is that the entanglement swap protocol, where individual nodes has to measure perform Bell state measurement, here we have shown that certain parameter range, even they don't need to perform Bell measurement. You can perform non-Bell state measurement, non-maximally entangled basis measurement, to achieve the same optimal fidelity. Okay, so I'll not go through all the details. You can have a look at it. And then what we have, so therefore, you see there is you can have this, you can save some amount of resource. So one is the, so 1 minus C is the, so C is the entanglement, or entanglement formation, or you can say concurrence in the non-maximally entangled state. So 1 minus C is the amount you have saved. Had it been maximally entangled state, this is 0, and you have n nodes. So this is the amount of entanglement that you have saved, and one can show that even if you have more and more noise in the noisy part of that entangled state, which is only one portion, this amount can be increased, this RV. Okay, good. So this is the saved resources. You can see that it will saturate, and for fixed number of nodes, as you increase the noise, the saved resource is also increased. This is what we mentioned earlier. Okay, good. And question is, where do you put these noisy entangled state? So if you put the noisy entangled state in the middle of the nodes, then you have less amount of, minimum amount of saved resource. But if you put somewhere in the end, you'll have better option. Okay, so I'll just close, just go to these, let me go to the summary. So there are, you can have also, advantage over this entanglement swapping scheme. So okay, let me just summarize. Where is the summary? Let me go to the, so let me just quickly summarize. No, I'll not. So this is some noise analysis we have done in case the pure entangled states are also noisy, specific type of noise. So there also we have seen that there is some amount of robustness in the scheme for the end node case. Yeah. Oh, it should have been this thing. Yeah. So let me summarize. So what we have done, we have started entanglement distribution of over a linear network. And as I said, this is important when you want to use this repeater case and generally the states are noisy. So what is the best option you can have? And there we have given some schemes where Bell state measurement is not the best. And in the n node scenario, what we have shown is that even with non-maximally entangled state shared, pure entangled state shared, where one is a mixed noisy entangled state, you can achieve the best fidelity which you can achieve with the standard teleportation protocol having maximally entangled states. So with this, let me stop, and if you have questions. Thank you.
Open for questions, but very few questions and very short questions.
So non-maximally entangled pure state and noisy entangled state is a mixed entangled state. Yes. Yes, Manik.
So you have shown one example, no, the where non-maximally entanglement basis measurement is giving
Better.
better. And the example you have taken this Horodoki kind of state.
Yes.
So now I'm saying Horodoki kind of state, the reduced part is not completely mixed.
Yes.
So is it possible that even for some state where the reduced part is completely mixed, is proportional I by 2, in that case also non-maximally entanglement basis measurement can give.
I don't think so. I don't think so.
That is not coming. That's
yeah, but we don't have the full proof of that. But I don't think if you have a the maximal what is that called, this I by 2 bay,
yes,
a reduced state, in that case the Bell basis measurement will give you the best result.
But there is some elegant joint basis measurement, no, that can give something.
Perhaps, but this maybe we'll have to see. Here we have not considered POVM or other things. So maybe that may give you better.
Any questions from the other side?
Ochunda.
Yeah, big question. I mean, so nice results. So you are saying you are gaining in terms of resources, for example, concurrence,
yes.
less concurrence, but that resource has to do with the resource of a state.
Yes.
So have you actually performed a resource theoretic comparison also of the resources required for the operation, for example, in order to achieve this protocol?
So we have not done the full analysis, but one particular case is, if this is again a presumption that non-maximally entangled basis measurement may require less resource, but of course this is a presumption.
Once you do that comparison, then you can claim,
yes.
I mean,
exactly.
That resource.
Exactly. So yeah, that we have not yet done.
Thank you, and we are running a bit late, so we'll stop here and a 15-minute tea break. And if you have questions, you can ask Professor Ghosh outside in the tea break also. But please come back in 15 minutes so that we can start the next session on time.
Sorry, always wait. Yeah.
Welcome back after the tea. And I hope some more people will join soon. But to constraint of time and not to delay the lunch, we have to start. So our next speaker is Professor R.P. Singh. Professor R.P. Singh is a well-known experimentalist, and he works at Physical Research Laboratory, Ahmedabad. So he will share his experience about the experiments done in his lab, and the title is Experiments in Quantum Communication. So I welcome Professor R.P. Singh to tell us.
So, okay, as you see the title, quantum communication. So, for quantum communication, you have to make quantum state and communicate through those states. That's the quantum communication. You prepare the state and communicate using those states. Simple quantum communication. And so these are my colleagues, younger colleagues who are involved in this work. Some are students, some PDFs, some are young faculty colleagues. Okay, so there are a lot of people involved, and it's done over the years, not like 6 months or 1 year. And we are part of Quantum Science and Technology program at PRL. So when you how do you prepare quantum state, and how do you take from one place to another place? So in the beauty of quantum communication is that it's through light photons. When you're communicating, it's through photons. And like quantum computer, you have so many platforms. Nobody knows which will succeed. But when it comes to quantum communication, you know that it has to be through photons or light. So that's the beauty of quantum communication. So you prepare quantum states. You can use weak coherent pulses, or you can use entangled photons, heralded single photons, or even quantized fields. So you can use all sorts of things, but related with light and photon. So weak coherent pulses, you take pulse laser, reduce the intensity in such a way that on average each pulse is having less than 1 photon. Okay? That's called weak coherent pulse. But it's not a single photon source when we're using weak coherent pulse. It's not a quantum source. It follows Poissonian statistics. So that's the beauty. It doesn't show any anti-bunching. It's still weak coherent pulse, uh, like laser, having less intensity, so that each pulse is having less than 1 photon. If you want to have a single photon, you can have heralded single photon source and entangled photon source using nonlinear crystal. You pass your laser through a nonlinear crystal, and this high energy photon of the laser gets converted into 2 photons, and these 2 photons, they are generated simultaneously, and you can measure correlation between them and show that they are entangled. You can measure polarization. If you show correlation, it will polarization entangled, or you can show correlation in some other variable, it will be entangled or correlated in that variable. So you have to measure that variable, in which variable you want to show that they are correlated. And how do you make entangled a single photon source? Because they are coming together, they are generated simultaneously. You detect one, and detection of one heralds the presence of others. So that's how you call heralded single photon source. So that's how you generate these things. Then you can have quantized field also. And when you say quantized field, when you talk of field in terms of field, you have amplitude and phase. That's how you define the field. So you can have amplitude and field, and that you can use again measuring of that quadrature components field and amplitude and phase. You can have a continuous variable quantum key distribution. And so this is light, so you can use fibers or free space, anything you can use. And you have to have detectors, you have to have optics, mirrors, lenses, all sorts of things. You can have detectors like single photon detectors, avalanche photodiode based, or you can have superconducting or single photon detectors, or you can have homodyne detectors. They are very simple, two photodiodes combined together and balance detection you do. So it's much cheaper to do when it comes to detection. It's much cheaper to do go for this very less expensive to go for continuous variable quantum key distribution. So as I told, you can have field quadratures or field quantized field as well as photons. Both you can use when you're using photons, measuring discrete variables like polarization. It is discrete variable when we are measuring using field and taking variable as amplitude and phase. You have continuous variable. And both sides we have prepare and measure protocols and entanglement based protocols. You can use both the properties, like you can prepare and then send, and measure other party can measure, and that's how you can develop the key. And when I say quantum communication, here we are talking of mainly quantum key distribution. Okay, we are focusing on one of the applications of quantum communication, quantum key distribution, because it provides security to communication. Okay. So here one can have entanglement based protocol, BBM 92, ECAD 91. There are other protocols also. These are the most popular protocols. And then that side also we can have prepare, measure, and entanglement based. Here you use two mode squeeze state for entanglement based. You can use Gaussian modulation here. This is 0 to where you modulate phase and amplitude both. And then here discrete modulation. You can modulate phase or amplitude. So both you can do. And this is the some of the experiments I have listed, which we have done in recent times in our laboratory based on weak current pulses. Then we have done this rigorous characterization of mean photon number per pulse using 4 detectors instead of single detector. Then we have done BB84, 200 meters and 300 meters with radar single photon as well as weak current pulses. Then we have analyzed like source side. What could be the leakage, information leakage, if there are imperfection on the source side, and detection side also, if there are some problem in detection side, what could be the information leakage. Both we have done. Then we have developed new quantum key distribution protocol we call coincidence detection protocol, and it gives much higher key rate than VP84 and decayestate protocol, which are the most popular protocols. And then recently we published this entire pulse coincidence detection protocol, and this combines the work of this, improves on this work, as well as it takes care of like it accounts the side channel thing and rigorous characterization. So this is like combines all these three works, this published work. And then we have used entangled photons also, and that was published like we have developed entangled photons. Then we have made it more robust. Okay, that published in 2023, and then we have used that entangled photon source for BBM 92 quantum key distribution protocol, and studied the effect of atmospheric turbulence, atmospheric aerosols, how it affects the key rate. And then we have done uh, fiber-based QKD with free space QKD, how to integrate that, working along with C dot, how to integrate free space, like we have done BB84 and this C dot, they have done COW fiber-based, how to integrate these keys with each other. Because ultimately you have to do quantum network, so you have to combine free space thing with fiber, then only you can have like global network. So that also we have done. So now working on entanglement swapping in free space atmospheric channel, that's what we are doing. And in CVQKD also we have done experiments, like we have done free space continuous variable quantum key distribution for 5 meters. For free space, this is the first experiment for free space. Okay, they have done for fiber, but these are the first experimental results which we have published. CVQKD in free space. We want to go for higher distance for 200-meter channel that we have made in PRL. We want to go for that using free space CVQKD. And we have made the indigenous turbulence chamber, and we are studying the effect of turbulence by changing the temperature difference along the chamber and wind velocity. We are studying like how the key will be affected. We are simulating the atmosphere using that indigenously developed chamber, and that will help us to simulate downlink and uplink both. So this is the general scheme for quantum key distribution. You prepare the state here. This is prepare and measure, and then you send. Okay, and this is prepare and measure protocol, general schematic for QKD. And you use single photon counting modules. You have to record the timing. FPGA, you see, field programmable gated array device. This is electronic board which controls the laser driving circuit. You have to randomly switch on the lasers. Okay, so that is done through this FPG electronic board, and this you process the data using the laptop or desktop, whatever. So this is the setup. Is we are now going to talk about this coincidence prediction protocol or interrupt pulse coincidence restriction protocol. This is setup is very similar to BB84 or decay-state protocol. You have 4 diode lasers. You randomly switch on. This is the we are doing in field. So this is the beacon laser. We use helium neon laser to align the system, and then we do the field experiment. Here 4 detectors. You know which detector will measure horizontal, vertical, or diagonal, diagonal. Depending on here, this is the beam splitter. So this is PBS. So this will horizontal, vertical. PBS, you know, it transmits horizontal, reflects vertical. So you know where it is going, horizontal, vertical. And here also this is lambda by 2 plate, you know where diagonal will go or anti-diagonal will go. So that's what you do in BB84. You measure in 2 bases, horizontal, vertical, and diagonal, anti-diagonal. And that you know where they will be going. And you know the timing here also when you are sending, when you are receiving, all the timing stamps are there in FPG as well as TDC. You have both sides FPG are there, so you have time records, and then you process. That's what you do. So what we are doing here in coincidence detection protocol, we are saying this coincidence detection is at the heart of quantum mechanics. That's what we say quantum measurement. We do coincidence detection. So in BB84 or decay-state protocol, we reject 2 photon pulses. We only consider key because of single photon. We are saying don't discard this 2 photon. Rather, you take the coincidence and use that for increasing the key rate. So that's how we are increasing the key rate. We published paper earlier, and then we do much more rigorous analysis using semi-definite programming. We show it's quite secure, and we could give the tighter lower bound for key rate, which was much more than BB84 and decay-state. So that's what we have done. We are not rejecting 2 photon pulses, rather we are using them to enhance the security as well as getting the higher key rate. So that's the essence of this protocol. So in general, how do you give the key rate for this kind of protocol? You have this QMU, this is the gain factor, this is the error correction factor, and this is the bind entropy, and this is the error rate, okay, bit error rate. And if you have like just 1 photon, if you are going to consider, this is mu is the mean photon number. So this is basically, you know, Q mu and E mu, you know. Okay, when you are doing experiment, because you are sending some mean photon pulses with mean photon number. So experimentally what you observe, only this thing you know, Q mu and E mu. But you don't know, like here, if you notice, this is Qi, okay. So if you are having just taking keys because of single photon, you will have Q1 and AEI1 only. And this is Alice and this is Eve. So this is information leakage, error. All the error you account because of Eve. In quantum key distribution, all the error you account because of eavesdropping. And this is information leakage to Eve from Alice. Okay. So that is given by this equation. And for 1 photon, you will see it will reduce to here He. Okay. So that you can put here He. So it will come to 1 photon, then you can have 2 photons. Those terms also you can add when you are going for coincidence detection. That's what we did. And these are the experimental parameters, pulse width that we have used, channel transmission we have measured, and then coincidence window and detection jitter, everything, all these parameters are there. We take into account. And then we do experiment as well as simulation also. So when you take like this formula I have shown already, when you can 2 photon, what will be the key contribution when you take 2 photon pulses? What will be the contribution when you take single photon pulses? And this combined thing, you will see it goes much higher when you combine both. And then we have done this key rate, this is simulation for different protocols. This is BB84 protocol, this is decay-state protocol. You see here they are much down. And then we have interrupt pulse coincidence detection protocol. What is interrupt pulse? It's like decay only. We are sending extra pulses like decay. So when we do this coincidence detection protocol, to make it much more secure, so we send extra pulses like decay. But just to differentiate from decay, we are calling it interrupt pulse. So we are sending randomly extra pulses just like decay, and that gives extra security to our coincidence detection protocol. And here you see that we get much higher key rate. And this is experimental results for 200-meter channel, quite close to theoretical result. We get much higher key rate, and one can go for higher distances if you use interrupt pulse coincidence detection protocol. And for this, we use semi-definite programming. You have heard already This is used for optimization. Sivas has talked about semi-differential programming. So you get better bound using semi-differential programming for the key rate. So basically, this is the key rate we define when we're using just one photon, when you're using two photons. So that's what this is the yield. Okay, this is conditional probability that LHC sends one photon, and given LHC sending one photon, what is the probability of detecting this one photon by the Bob or receiver? And then, as you know, this gain is basically gain factor is joint probability of sending and detecting one photon by parties. So, and so this is the key rate, and then you optimize this function basically, okay, using semi-differential programming given these conditions. And for two photon, we take into account, you optimize this function using semi-differential programming, and that's how you get all the results which I have shown. And once we have done like coincidence distribution protocol and all, we thought we will do this for entanglement distribution. We have shown that we have prepared this entangled photon source and then distributed across 200 meters. And then this is the like filled like setup. This is chamber of Ellis, Bob, and then we are using reflector because we have only two buildings in our Thaltes campus which are 100 meters apart. To make it 200 meters, we do the reflection. Then we have done for 35 meters also. So we have measured entanglement when we distribute photons, this pair of photons for 35 meters as well as 200 meters. And here we are using a Sagnac configuration, okay, Sagnac interferometer for making entangled photons. But we have used another setups also for making entangled photons. It's not essential that you have to use this setup only for making entangled photons. There are so many schemes which are very robust and generate a high number of entangled photons. You can use that. And so that's how we distribute after making entangled photons. We distribute this to Ellis and Bob, like two parties who are going to develop key or who are interested in communication, and then they make measurement on those photons to generate key. So that's what we have sent them 200 meters apart, and then we measured the Bell inequality, okay, by measuring the coincidences. So this Bell parameter is quite good. That's what we measure. Visibilities are quite high for this correlation curves, okay, and so Bell parameter. So that's what. So they are entangled. Even after sending 200 meters and 35 meters, that is measured. So now we have measured the entanglement, and we can make these measurements on these entangled photons, this pair of photons, to generate the key also. So we have generated that, and we have done this VVM92 protocol, and we get this kind of, we combine HS because we are generating HS plus VV kind of entangled photon pairs. So we get maximum on this, okay. HH plus VV basically equivalent to DD plus A also. So we get this kind of thing, and that will give you the key. Then you do the error correction and privacy amplification to get the secure key rate. This is shifted key rate. Okay, so you get the secure key rate. Up to shifting, only quantum mechanics is involved till late. Beyond that, use classical algorithm for error correction as well as privacy amplification. So we have studied the effect of atmosphere also. We get these atmospheric parameters from our space and atmospheric census division, and we see that atmosphere really, it's obvious, but it affects the key rate. When you have more number of aerosols, the key rate will be less. Okay, when you have less, key rate will be higher. So that we have verified. So we have done this key distribution with entangled photons produced. So as Subhasis was talking, you can have like non-maximally entangled state. So how much non-maximally entangled state you can afford to have this key distribution? That's what we wanted to study. That's why we use this HM interferometer, and using HM setup, you see here, this is HM setup only. Okay, here this beam splitter, and these two photons are coming. So HM, it's used for making indistinguishable photons, two photons which are completely indistinguishable. So yes, just over here last. So then you just change the, like, you discriminate in polarization using half a plate and BS. So you can have entangled photons, and all four kind of Bell states you can make using HM setup. So we have done that, and beauty is that when you go away from this dip of HM, okay, this is the dip, when they're completely indistinguishable. When you go away from dip, they become non-maximally entangled. Okay, when they are here, you get maximally entangled. When you go away, they become non-maximally entangled. Yes, becomes lower. And then because you have two photons, you can make measurement. You can all the things you can do. Cuber, you can change quantum bit error rate. You can have control over S parameter by going away from this. This is translation stage. Just you change the delay and you can go away from the maximum. So that's what we have done, and we have plotted these things. So you see that a Cuber and S relation, and this relation has already been derived, but we did this experimentally. And so we see that it really follows this kind of relation. This is error rate, and this is Bell parameter. So we have done that. Cuber we have changed and see that yes, it changed. Okay, so even this you see that error rate is like error threshold is 11% for BBM 92 protocol or entanglement protocol, and you see even at 11%. So even beyond 2.2, if you have like 2.2 plus, you have anything like Bell parameter, you can do this uh, quickly. So then we have done like mutual information between Alice and Eve and Alice and Bob. And you see here, you can, when this is Alice and Bob and this Alice and Eve. So for positive key rate, this Alice and Bob mutual information should be higher than the Alice and Eve. Okay, and then only you can do. So if you are up to 4% something, 4.2 bit error rate, you see it's coming everywhere same. So you can do this key distribution if you have, and then you don't have to do anything. You know the Bell parameter just by looking at the Cuber. You know the Bell parameter. So that's the way you can go towards like device independent quantum key distribution. This is ongoing work, and I think Sivasir Ghosh, he is using non-maximally entangled state as well as mixed state, and he can help us to improve on this work. This is ongoing work. This is already in archive. We are working further to improve to submit in the journal. So this is the work which I was referring for making the network. You have to like combine free space and fiber keys. So we have used a trusted node, and then this is the key dot thing. And they have used UW, and they have like key K1. And then we have like PRL. We have then free space. We have used BB84, and we have K2. Then we can have like this is trusted node. We can have K2 jar K1. Both are having now just another jar will get the key. Both parties are having same key, and we have used it for encryption and like transfer of message. So you can, that's the way to go for network, and these are the like future plan. And we bet on like photonic quantum computing. One of our colleague at quantum science technology program is doing focusing on photonic quantum computing, because we feel that that will be the best way, best bet for like secure communication as well as computing. You can seamlessly connect secure communication and computing if you go for this photonic quantum computing. You can have seamlessly. Thank you.
Thank you, Professor Singh, for a nice talk and elaborating so many things and within time. And now it's open for question.
So you usually use pulses which contain one single photon for QKD, right? But in your case, you have also used pulses with two photons, and that enhance the key rate.
Yeah.
But your the mathematics doesn't exclude using even pulses which has three photons or four photons.
So because some other kind of attacks may happen, like unambiguous state discrimination attack will be possible. There's some other. That's why we have limited up to two only. We have not got earlier work. We took into like three pulses, three photon pulses also. We got much higher key rate. Then we realized that this is not safe. So that's why we are keeping it to two only, and that's like quite secure. Same security as BB84, proven security, as well as it gives hierarchy rate. So that's why we have not gone for earlier optics continuum that we included three. That was not correct. So we have improved on that in our latest SLA.
Okay, thank you. you, Professor Singer, for an interesting talk. I also would like to ask about this point. If you may elaborate a bit more on the QKD using two photons and the essentially possible attack that you may have with the photon splitting. Okay, so is the hardware enhanced to include say photon number resolving, or so how you deal with the photon
We
number?
take care of photon number. It's like secure against photon number splitting attack. We are not saying we will be always taking two photons per se. We are taking like single photon as well as two photon. We are not discarding key like discarding two photon events. Rather, we are taking two photon events also to generate the key. That's the beauty, and it's safe against photon number splitting attack. Yep.
So it's in the model of the key.
Pardon?
It's in the model of the key.
Yeah, it's in model. It's
Yeah,
in
we
between.
like to
Yeah,
see the
yeah. You can check the paper. That's paper. Yeah. Detailed analysis.
So when you take this two photon generation, do you consider a specific state encoding for the two photon things?
No, it's the same BB84 kind of thing. Correlation state encoding. That's all.
So what happens if I consider specific state encoding so that this attack will not change it much? Is that possible?
When what do you
Like
mean by when we are doing
you
weak
know,
coherent pulse kind of thing? What do you mean by specific state encoding? So
no,
not.
I mean, because weak coherent pulse it may not be. Like,
Yeah.
if I take some entangled.
So entangled becomes completely different ball game. Then yeah, here weak coherent pulse specific state that's becomes like slightly.
No, I was thinking that people talk about these topological states where the noise etc. may not affect people.
Yeah, that's also we are doing the topological thing also. We are using OM states. I have not talked about. So we are using that.
And about this, the turbulence. So you said you have taken data from your colleagues there. So what specific?
Not turbulence, that is atmospheric parameters like aerosol concentration and all those things, how it varies from day to day. They have hourly data of aerosol concentration.
Okay.
So we have that data, aerosols data for each date. So we can see that when there is high concentration of aerosols, so you will have less. It's not turbulence data.
Any question from the other side? Questions from students?
So this is for students only. Please read it and keep your aim high.
The Michelangelo code.
Yeah, Michelangelo.
That's for students, not the dog.
Yes, sir, here in DIQKD, you showed that in DIQKD, the measurement should be done in a specific time window. So how do you ensure that in that?
Time window we like very specific. This any QKD you do, you fix the time win. 2 nanosecond, 1 nanosecond you can fix. So it's done during that time window only. That okay.
Yeah, other question, comment. So if not, let's thank Professor Singh for a nice talk. And I invite the next speaker of the session, Dr. Bhaskar Kansari. Dr. Kansari is from IIT Delhi and is an experimentalist who also works on quantum communication.
No, that's fine. I think. Can you make it full screen? It's very slow. First. Oh, 2 times. Fine.
the pointer, so that pointer is very trivial actually. So that the pointer, this is for checking the size. It's two body problem. No, not this. You could cut it maybe, no? This one is not required. The back one is mine. Yeah. Yeah. Okay, so good afternoon, all of you. And first of all, I would like to thank the organizers, especially Professor Pankaj Agrawal, for taking on the pain of inviting us and giving this nice hospitality. So I will be talking about entangled qubit sources for quantum secure communication and imaging. So the idea is to give you some idea, some basic aspects of the sources which we are using in our lab, and then their applications in quantum secure communication, but also some part of imaging, which probably I will come to at the end of my presentation. So we have been talking about quantum communication. If you look into broadly, there are several areas quantum communication technologies cover. This includes not only quantum key distribution, which has mainly been talked about, but also areas like quantum teleportation, quantum repeaters, quantum random number generators, and also in fact two important areas which are distributed quantum computing and distributed quantum sensing can be possible using quantum communication. In fact, one can also use quantum communication for precise clock synchronization. Our group at IIT Delhi is mainly focusing on some aspects of quantum communication, which includes free space quantum communication, where our focus is to do entanglement based QKD, use partial coherence for improving the key rates, and also to use them for quantum imaging. We are also working in fiber-based quantum key distribution with a focus of telecom compliant QKD using both prepare and measure and entanglement based protocols, and also trying to focus on building a quantum network under National Quantum Mission. And I will come to this toward the end of my presentation. In fact, one of our focus is to develop single and entangled photon sources with majorly with high brightness and with high purity. And in fact, with material science colleagues, we are aiming to develop superconducting nanowire single photon detectors with PNR resolving capabilities. So as of now, I will talk mainly with these three things today in my talk. So already Professor Singh mentioned about QKD. There are mainly two types of QKD we are focusing in discrete variable. One is prepare and measure kind of QKD, which essentially uses Alice as a transmitter. It prepares the states, sends them through quantum channel to the Bob. Bob makes a measurement, and then they can use certain protocols to set up the key. Entanglement based QKD is slightly different. It essentially uses, for the longest distance, it can use the source in the center. Both photons are traveling in opposite direction, so they basically can travel twice the length if you look the state away analogy. And then Alice and Bob both are receivers. They are receiving the states and using some protocols to set up the key. These are some of the features of both of them. I will not go into the detail. The major aspect is that in the previous case, like in prepare and measure, we need to have trusted node or secure nodes to go for long distances. Whereas in case of entanglement based QKD, if one can develop repeaters or memories, which is currently quite in focus, we could actually go for long distance trusted node free communication. Entanglement provides an extra degree of freedom of security, and even a hacked source can produce secure keys. And also it is quite compliant with many entanglement based applications such as swapping, quantum teleportation, and also repeaters. So basically I will give one example of each which we have been doing so far. So in the beginning we started with what we call differential phase shift QKD, and with DRDO we made a QKD scheme, and we demonstrated it between Prayagraj and Vindhyachal, which were the two cities separated by 100-kilometer underground fiber. The length of the fiber was about 100 kilometers with losses about 26 dB, and we could achieve a key rate of about 10 kilobits per second with less than 9% QBER. So this was the first demonstration of intercity quantum communication in 2022. Then we asked the question whether we can go for even longer distances by improving our sources and detectors. So we looked into all the sources which are producing QBER, tried to minimize them. For example, we looked into the line width of the laser, the dispersion of the medium, and also the interferometer leakage of the photons. And the detector side, we use superconducting detectors, which have higher quantum efficiencies and low dark count, which reduces the QBER. And we could go up to for more than 300 kilometers, which we call trusted node free, because otherwise we could have put at least 2 trusted nodes to reach that distance in 2023. In fact, the kind of QBER we achieved, which was less than 1.5%, was higher than whatever has been reported so far with this protocol globally. So this is one way to do QKD, which is prepare and measure. But now we are more focusing on entanglement-based QKD, and already the process by which we generate entanglement has been mentioned in the previous talk. It is a process called spontaneous parametric down conversion. One can do either type 1 kind of configuration where we have collinear and non-collinear photons coming out in the following profiles. And if you use a type 2 kind of bulk crystal, you actually get two cones which are having different or orthogonal polarizations, and at the cross sections the polarization is undefined, which can be used as a polarization entangled source. In fact, this has been well studied in past, and the entanglement generation, entanglement characterization, and its applications have led to the Nobel Award in 2022 to these three gentlemen. So in our lab, we are working certain type of entangled photon sources. We are using two sources based on Sagnac based geometry in type 0 and type 2 configurations, which are basically for 810 nanometer, which we typically use for free space QKD. And we also developed one all guided wave PPLN based entangled photon source, which is essentially in telecom wavelength. And in all these sources, if you look into, we have higher visibilities than 87%, and also our Bell parameters are more than 2.6. So now we use one of these sources, that is the telecom wavelength one, for distributing entanglement, and this is done by putting it somewhere in the lab and using fiber spools to propagate for different lengths. So we actually tested different lengths because we wanted to check that how the distance changes or degrades the entanglement. And as you could see here, this is the visibility measurement at the source, and as you go away, you actually the entanglement remains. It's not working properly. Yeah, it's not okay. Sometimes it is working. So you see that we can go up to 100 kilometers with the kind of coincidences we have in the beginning. And if we could actually improve our source, we could have gone up to 200 kilometers or so. As you could see here, that the visibility is more than 70%, and we can violate the Bell's inequality for that case. And then we do the QKD, because our goal was to go for a rate higher than at least 1 kilobits per second. We can go up to 50 kilometers, where our QBER was about 2.7, and our key rate was 1.43 kilobits per second. We also tried to see if we could Yeah, so we also tried to see if can we test it on a deployed fiber, and we took a fiber from our computer science department, computer science center, which essentially takes care of internet within IIT Delhi campus. And that fiber was though quite old with very high losses. It gives us a length of about 8 kilometers underground fiber within the campus. So we put one photon through it, the second photon through a fiber spool of 10 kilometer, and we could show that we could get a key rate of about 2 kilobits per second with a QBER of less than 3%, showing that entanglement based QKD is quite compatible with field deployed telecom grade fiber and can be very easily scaled for even longer distances. Then the next thing we wanted to understand is that, which is one of the biggest problems, is can we co-propagate quantum and classical signal through the same fiber? As we all know that the quantum signal carries the flying qubits, that is the photons, the classical signal also is required either in post-processing or even in synchronization or even doing the real QKD, real communication using those keys coming from quantum channel. So if we multiplex both quantum and classical signal through the same fiber, since both the signals pass through the same or identical ambient conditions, they automatically compensate for polarization or time delay fluctuations, which gives us quite a benefit experimentally if we could do so. At the same time, it can be not only reducing infrastructural costs, increases the bandwidth, but also can be useful for high precise clock synchronization. And our goal is to do this at C-band itself so that both could incur least losses and could use the same off-the-shelf kind of components. So we do that. We first look into the sources of noise which come when we put an intense classical signal and a weak quantum signal, and majorly it comes from the scattering. And we characterize the Raman scattering, which is having the lion's share in this scattering part in both forward and backward direction. So you could see that we use a fiber spool of 50 kilometers, measure both forward and backward direction. And as you could see here, when our classical signal is at 1560 nanometer, we could get higher backward noise, backward Raman scattered noise than the forward noise. That means that we should preferably use the forward geometry. We then check that what happens to the coincidences generated due to this classical signal, and we find that somewhere at ITU 25 we could actually put a quantum channel because the coincidences are minimum at that. Now we send both through the same fiber, that is ITU 2022 and ITU 25, and you could see that and increase the power of our classical signal. And you see that we could go up to minus 16.82 dBm of classical power, till which the Bell violation can still be made. That means we are operating at 21 dB higher than the standard classical communication power, which is currently used for communication. So we can do both together on 50 kilometers fiber, and also, in fact, we can have more classical channels or quantum channels together still within the requirement of the standard communication. Now I would just change the gears, and I would like to talk something about partial coherence, because I mentioned that we are using partial coherence also as a useful tool for free space communication. So the idea is the following. Classically, in optical communication, it has been well studied, thanks to Emil Wolf, his co-workers, that in a turbulent medium, if we send a single mode coherent beam, it scatters a lot because of high coherence, interferes with itself, produces speckles, and that way it deviates from its main path significantly. Whereas if we could send a partially coherent fields, which are multimode in nature, have very less coherence, so the scattering would be less and its probability to reach detectors would be more. So that means for a turbulent media, partial coherence may provide some benefit over fully coherent beams. So we want to generate partially coherent photons now, biphotons, and that is using the process of SPDC again, where the pump we want to be multiple spatial modes, that means partially coherent, and want to see if this partial coherence travels from pump to the down converted photons, which we can use either for communication or it can be used for quantum imaging or quantum sensing applications. So for that we consider a model beam which is called Gaussian shell model for the spatial coherence. This is a very nice mathematical model, well proven in past, because here both intensity profile and the coherence profile are Gaussian in nature. So you could see that we can measure, we can use this A parameter, which is the ratio of coherence width to the beam width, as our defining parameter of degree of coherence, and that way we can range the value of A from 0 to 1, which is from incoherent to fully coherent. So we use it, and experimentally we can generate it by killing the spatial coherence of the laser by focusing it on a random media, which is a rotating ground glass diffuser, and then this field propagates as a natural light field thanks to Wenstedt-Zernike theorem, and one can measure the coherence properties at the plane where SPDC is put, that is the crystal is placed. So you could see that our beam size is remaining roughly same, whereas our spatial coherence can range from very high value to very low value depending on the lens translation. So we use this, and in fact we also look, can we control the polarization aspects, and we make a tunable polarization and partial coherence source, where partial coherence control comes from the size control, and the polarization can be controlled by either mixing two orthogonal polarizations or can be by controlling the coherence. And that way we can get a degree of coherence variation from very high value to nearly partially coherent value, and also the degree of polarization control is achieved from near 0 to 1 value. So we use them. We experimentally first look that if we do use this GSM beam now focused on a crystal which is using a Bibo crystal, bismuth borate, and looking into the profiles using a EMCCD, theoretically we should expect that as we decrease the spatial coherence, we should get a more fuzzier and asymmetric profile, which experimentally also validates. And we can carefully choose the parameters so that we are not very much fuzzy, because otherwise we will not know where the photons are being generated and where we are in the profile, but also we can have a good partial coherence with a smoother profile as well. So we use that, and then we try to look into the transfer of partial coherence by measuring the first order interference of the photons. For that we make a double slit interferometer in the biphoton arm. This is the type 2 scheme which we are using here, and these are the interference fringes which we achieve for different spatial coherence values. So what we see is that essentially our spatial coherence decrease of the pump decreases the spatial coherence of the photons as well, which is measured not only by the visibility but also by the conditional probability distribution, where we keep the position of the signal fixed and measure for Idler for different coherence parameters, and we find that the transfer of spatial coherence properties in SPDC process from pump to downward photons happens. In fact, this gives one more interesting result, which says that if we want to do any single photon interference, which is well known from the time of, I think, Dirac, that if we do so and using a double slit, then the coherence spatial coherence of the photons matters. If it is very low, probably we will not get any interference fringes, and we have to have a sufficient spatial coherence in order to obtain the single photon interference. Then we look into the effect of entanglement, because this is a very crucial aspect, and we are using here a particular geometry which is called paired crystal geometry, where we have put two crystals, identical crystals with their optic axis orthogonal to each other. Each gives us a profile, and the superposition of these two decides the entanglement. However, as you remember that our profiles are asymmetric. So in that case, the total profile still has a distinguishability, and that distinguishability kills the entanglement as we go smaller and smaller in spatial coherence. And one way to get it back or recover would be to select a few modes rather than all possible modes by putting some aperture or some small pinhole, and we do so. When we see that we reduce the size of pinhole, we could actually get a situation where we are still within the Bell violation for all possible cases of spatial coherence. That means we can get entanglement enhanced partially coherent qubits. We test it experimentally as well. We use our Gaussian shell model scheme, pass it through our type 2 BBO crystal, and look in EMCCD what kind of entanglement we achieve. We basically measure S parameter, and by putting different size apertures, we see that for the smallest aperture, we are within this Bell violation regime of more than 2 for all possible cases of degree of spatial coherence. So the recipe is, we have to start with multiple spatial mode entanglement generation and single mode detection, which will lead to these kind of results. We look into now one of the applications of that is on ghost interference or ghost imaging. In fact, ghost interference has been well studied in past by several groups. With partially coherent light, the results which are well known are that the visibility, which is given by the contrast, and the quality, which is given by the resolution of the pattern, have a trade-off. That means if we reduce the coherence width, we essentially get a better resolution but a lesser visibility. Whereas if we go for higher and higher coherences, our visibility is higher but our resolution decreases. So at the same time we cannot get both. Whereas in case of SPDC, people have also done ghost imaging and they have found that at the same time both visibility and quality could be the maximum. However, our interest is to have partially coherent beam with maximum visibility as well as maximum quality. That means we need both to retain both features of partial coherence as well as the quantum features. And for that, we look into a particular scheme where we use our partially coherent entangled qubits and try to do a non-local interference. That means in this kind of ghost interference geometry, we use a single slit in one arm and a wire in the other arm, so that non-locally this will form a double slit. So this non-local interference we test, and we found theoretically that our visibility and quality, that means the number of fringes or the resolution, both can be maximum for different slit sizes which are shown here. We tested experimentally very recently, and here as you could see that we are using the same source, but now we are putting a aperture and a wire in different arms. And for all possible cases of the degree of coherence with maximum and minimum value, we see that we have high visibility and high quality for partially coherent region also, which can be used for for testing turbulent media or imaging through turbulent media. So we are looking for more activities in this direction. Now I would like to tell something about our project. So we are starting a project under National Quantum Mission. It is named as Towards Trusted Node-Free Hybrid Quantum Secure Communication Networks. In short form, we call it Tehqiqat, which essentially means to investigate through research. So the goal is, we have a consortia of 5 institutions: IIT Delhi, IIT Roorkee, IIT Jammu, ISC, and IISER Bhopal, where we are trying to set up a physical network, quantum network, covering 4 states. So this picture is coming over it somehow. So there are 4 states, which is Delhi, UP, Haryana, and Uttarakhand, connecting IIT Delhi to IIT Roorkee. So we'll have 6 nodes, 3 within NCR region, and 1 at Sonipat, and 2 at IIT Roorkee. And the goal is to have a hybrid quantum network, which includes not only entanglement based protocols, but also prepare and measure protocols, use free space QKD at IIT Roorkee and IIT Delhi, along with fiber QKD within that 300-kilometer long network, and also discrete variable with a continuous variable operation. So that way we are trying to test, because these are the only available QKD solutions so far, and we believe that we need an interconnection, interoperability between them, and that can only be possible when such kind of hybrid networks could be set up and tested. The hybrid, so we would be looking into different such combinations, the network architecture, and hopefully it would lead to some aspects of quantum internet in near future. So I think I'm finishing now. So to summarize, we discussed about entangled photon sources and fiber-based QKD in the lab and in the field. We have worked on partially coherent qubits, and we have shown that how coherence and entanglement can be used for developing such kind of qubits. Finally, we could recover entanglement in case of partial coherence, and looked at one of its application in quantum interference, which would later on would be quantum imaging. So I would like to thank my team members and the funding agencies, DRDO, DST, NQM, and Institute of Eminence for all the support. So thank you very much for your kind attention.
Thank you, Bhaskar, for a nice talk, and now it's open for questions.
After the nice talk, so
Thank you.
please elaborate on the need and advantage for having a hybrid space as well as fiber network. I mean, why do you require it, and I mean, what is the motivation?
So the motivation is that we have, that we have satellite-based communication for connecting long distances. Internet, for example, over intercontinental distances. But at the same time, we need local area networks or metropolitan networks, which will not be with the help of satellites. In fact, not even with free space, because free space is having always the problem of availability. So the only solution could be fiber in those places. Now the point is how can one connect these satellite based things with the local fiber based things in a trusted node free manner. So well, so we have to somewhere connect physically, you know, and that would be a security loophole if it is a trusted node, because one is, so imagine that if it is 810 nanometer and 1550, which are different wavelengths, how to mix them. So we have to find ways to do that. And if both are telecom, which is one of the possibility, because telecom wave based free space QKD is also possible, and many times it has been shown that it is way more robust than free space, then still we need to show somewhere the connection between them in order to go for these topologies with the satellite based QKD. So this is the idea behind that.
I have three short questions.
Yes, yes, please.
One is that to control your coherence and reduce it, you have played with the transverse coherence. Does the
in the second part,
yeah.
Yes. So we are only working on transverse, special
longitudinal.
No, not longitudinal, because longitudinal is related with the spectral width of the source. So there is a relation between temporal coherence and spectral width, and a spatial coherence and the beam sizes. Right. So we are looking into spatial coherence because that is something through which, because see, the photons which are traveling in free space still follow the classical of propagation. You know, the optical beams are there. So we know that from classical optics that which are the best robust beams which are passing through turbulence with lesser losses. So now they are the photons. So that is the spatial coherence, that is our multimode nature, which comes into picture in transverse nature only, not in the longitudinal nature.
Okay. The second question is that S parameter you have shown, even one curve showed that even for zero coherence, you get a space parameter above.
Yeah, in all cases, even for incoherent beams. I mean, we are not the first to show that. In fact, theoretically, Boyd's group, for example, has worked a lot in that direction very recently. They have shown with LED, for example. So they are using LED, which is itself not a fully coherent source. But with that also, you can get, even they are trying with sunlight now. That can be used sunlight or white light kind of sources. So, I mean, there are ways where people are trying to do. The idea is that why we really need a laser for that. Okay. Can we work with a different type of source?
The last question is about your imaging. So have you tried to image an object of arbitrary shape by imaging?
So far we are doing interference. So we are using a non-local double slit and trying to look into the fringes. The next step would be to put some object and to image it. So that will be the next step. No, not yet. Yeah. Okay. These are the results just maybe last month or so.
For the interesting topic.
Yeah, thank you.
The transformation that you have in the free space channel actually involve also, say, a transformation in the photon statistics, or in a way, the longitudinal thing. So, for instance, you
transverse coherence, not longitudinal, transverse.
No, indeed. If you go the long way, then you have essentially that you have a phase modulation on the transverse plane that essentially then is transformed into amplitude modulation, but then you have modulation again and again. So this process can be essentially pictured as a multiple phase planes on the exponent, and so get to the log normal distribution, which affect the temporal shape. While what you have shown is the essentially Areki disk, so the rotating disk that was used for essentially changing the statistic of photon from.
So talking of these ones?
Yeah, the example you made on say having reduction on coherence with the spinning disk.
Yeah. Rotating ground glass diffuser.
That's originate from a paper by Tito Arecchi of 1965. Okay. And have shown that change of the statistics from Bosonian to Bose time, okay? But it's only, say, getting to that, not to the actual transformation in the longer channel. So I wonder if you...
So far we have not put our photons in any channel. So we are still in the lab. We are still doing, because this is first step was to prepare the state. So the state is ready now. And we are working on a free space channel, which is currently up to 100 meters, but we are making it up to 1 kilometer, where we will be making all these tests in the space now. So probably then in that point of time, we will look into our analysis again to see that what happens when we increase the length of the quantum channel. Yeah.
Oscar, you are saying that you want to do trust node free quantum key distribution and that also hybrid. So
we said we are doing some communication which will be towards trusted node free. It is not yet, because trusted node free operation requires repeaters. And since in NQM actually the goal is that there are some groups which are working on memories and repeaters, some are working on different aspects, and then once their outcome comes, they will try to operate in such a way that we could go for a final joint activity.
If you want to do hybrid trust node free, then you have to have all along entangled protons either for satellite or
yeah. So these are all so whatever we are doing all is entangled, except the previous last two projects which are from DRDO. Rest everything is based on entanglement only. Yeah.
Is there any question from the student side? So if not, let's thank the speaker.
Thank you very much.
You have to contact volunteers outside, okay? If you don't want to miss your lunch, okay? Because you will be taken somewhere for your lunch. So all the participants first, the speaker we will take later. All the participants, please contact volunteers outside. They will help you to go to the lunch venue. Okay. So if you miss the bus, then you'll miss the lunch. Okay? Very good.